The next homework assignment related to pumps is due on Wednesday, which is the same day we're going to have our first midterm exam. Has anybody tried to download and install Water Gems based on the email that I sent you? Okay, so give me a thumbs up if it worked. Wow, frankly, I'm shocked. That's great. Give me a thumbs down if you tried and it didn't work. Okay, they must have got their act together over there because earlier in the semester I think there were a couple of roadblocks and it sounds like it's all sorted out. So, what a relief. All right. So regarding the exam on Wednesday, I'm going to provide you with an equation sheet, and let me show you where you can find that if you want to start to look it over and familiarize yourself with the formula sheet. It's on Blackboard right now. So it's 4 pages long. It's a really long formula sheet. Let's just very briefly look at it down here at the bottom, equation sheet. So I think you're going to already recognize a lot of stuff that's on here. You've got the energy equation, momentum equation, continuity, local losses, Darcy-Weisbach equation, and so on and so forth. You know, maybe it would be a good test to have you name all of these equations. I bet you could, right? Do you remember this one? I showed you, but we didn't use it. So anyways, so there's lots of formulas, a few tables of, for example, equivalent sand roughness, Hazen-Williams friction factor, Manning equation roughness. We're going to be talking about this stuff today. This is related to when you change things on a pump and the performance that applies. So some of these formulas, obviously, we haven't got to yet. It's going to be later in the semester. Hey, I recognize this. All right, what's this related to? Water hammer. How'd you know that?
Been studying.
You've been studying. That's what I like to hear. All right. Then some of this stuff isn't going to be until later in the semester. You know, this page, 3 and 4 is all open channel flow stuff. So I'll still put it on there, but I don't expect you'll need the third or the fourth page on the exam. So I'll provide that for the test, and in addition to that formula sheet, you can bring your own page of notes. Now you're going to have to use Excel at some point on the exam, and I haven't decided yet whether it's going to be a loop problem or a 3 reservoirs problem or a pipe diameter sizing problem. There's been a few things this semester that you've had to use Excel for, and I've provided templates for those. You can't use the template on the exam because I just don't want you to plug numbers into a spreadsheet I made and let's call that a test. It doesn't seem quite right. So what I want to know is whether you understand the material well enough and the procedure and the process and the underlying theory well enough that maybe with a little hint, meaning what you put on your formula sheet, like a reminder to yourself of maybe what are the steps, that you could generate all that on your own. So, so that's what I intend for you to add to that page of notes. I'm giving you all the formulas that you could need, but you know, if there's some process-related reminder that you want to put on that page, front and back of notes, then I think that's a good idea to supplement what you're going to do with Excel. So for the Excel problems, you're just going to be starting with a blank workbook. I'll be standing in the back of the classroom to make sure nobody's doing message chat to each other or anything nonsense like that. So any questions about the exam? No? All right. We're going to continue talking about pumps today, and then I've got another nodal method practice problem just to refresh that in your mind. But where we left off last time was I rushed through the solution to this problem. And because it was a rush, I'd like to revisit that because I think it's valuable just to reinforce what's the problem-solving strategy to find the operating point. Determining Q is part of this problem, but also calculating the electricity that's required by the pump, because we didn't have a previous problem where we applied the power equation or these cumulative efficiency factors. So, okay, the overall structure of the problem is you're given a pump curve, which comes from a manufacturer. It maybe is an equation. It maybe is a figure. If it's a figure like this, you could make an equation out of that figure. And in fact, you have to do that on the homework assignment. I gave you some hints on how to turn a curve into an equation. So in this example, you've got a formula that describes how with an increasing flow rate, the head that's added by the pump decreases. Because the more water that's going through it, it's not increasing as much pressure on the upstream end of that compared to the downstream end of it. So that's part of it. And the other part of it is we have to create what's called a system curve. And a system curve is just simply the energy equation rearranged in terms of solving for H sub P. So this formula and this formula are very closely related. It's just we've algebraically isolated H sub P on the left-hand side of the equation. And then on the right-hand side of this equation, the delta Z is simply going to be Z2 minus Z1. So in this case, you can see the elevation difference is 12 meters. And then on the right-hand side of the equation, we're canceling out the velocity head terms at both the origin and the destination. Because, number one, velocity head is relatively negligible. But then the other factor is that here in the reservoir, the water doesn't have any velocity head. So in this formula, the velocity head's been neglected. And so since this is a jet where the water is being discharged into the atmosphere, the pressure of the water at location C and at location A is the same. So the pressure heads cancel out. So the pump head here is only related to the elevation difference and then the losses through the pipe. So the first term here is the friction losses. The second term is the local losses. So if we go back to that calculation, what we did was determined the system curve and set it equal to the pump curve and solved for the operating point, which was 0.144 cubic meters per second. And then we substitute that flow rate into either one of the equations for H sub P. We could substitute that into either the system curve or the pump curve. That flow rate will give us the same H sub P, which is either from the perspective of the system curve, that's how much pump head is required to be added in order to achieve that flow rate, or from the perspective of the pump curve, that is, for a certain flow rate, how much pump head can the pump actually contribute to the system. And for the flow rate that we've calculated, those two values are one and the same. So that's what we did. We found the flow rate, we found H sub P, we answered this kind of tangential question, how long does it take to pump 1,000 liters of water? So we knew the flow rate Q and solved for the time that's required to pump a certain volume of water. Now, the data that we had from the problem statement was that the motor is 65% efficient and the pump is 80% efficient. So if you multiply those two things together, the combined efficiency of 52%, that means that if you put in 1 kilowatt of power, in electrical power to the motor, then what comes out of the pump is only 520 watts of power being added to the water. So there's a big reduction in the amount of energy that goes in versus how much comes out of this combined pump motor system. And so the power equation, which takes into account the efficiency, we have to put in the flow rate, the unit weight of water, the pump head that's added, and divide by the overall efficiency. So what that tells us is that electrically, this is going to be requiring 48.5 kilowatts of power in order to add a certain amount of energy to the system that will enable 0.144 cubic meters per second. So just to put that in perspective, does anybody know, like if your house has the AC running, like if the heat pump is switched on, do you have an idea of just ballpark how much electricity you're using at your house? It's usually between 5 and 10 kilowatts that you might be using. So here what we're saying is, you're using like 10 times, like between 5 and 10 times the average house just to operate this pump, which is a lot, but then keep in mind that you're lifting 144 liters per second. So, like, you know how heavy a 2 liter of soda is. So what if you were lifting 144 liters of water every second, and you're lifting it 12 meters and overcoming enough pipe friction that the total pump head added is 17 meters. So it's kind of like you're lifting every second 144 kilograms of water a distance of 17 meters. So, I mean, that's a lot of energy to do that much work. It makes sense here that it'd be about 50 kilowatts because that's not an insignificant quantity of water. Okay, so that was just a little bit of a review of that example from before. Now what we're going to be talking about today is when we make changes to how pumps are operated. So for instance, if we have a pump and we rotate it at a different speed than it was originally operated at, or if we have related pumps that have similar shape, they're made by the same manufacturer, but they have a variety of different options. You can either put in a small impeller, a medium impeller, or a large impeller, sometimes into the same housing. Or the thickness of the impeller is sometimes adjustable. And these related pumps can be understood with what are known as scaling laws or affinity laws. And that's just that if you understand the performance of a pump under one set of conditions, then you can calculate numerically, because of these scaling laws, how it's going to perform at a different range of conditions. So these formulas, I've screen captured this out of the FE equation book. Your textbook also has these equations with different variables, but this is just to get you familiar with how it looks from the FE reference manual, because it's likely you could see a problem related to this on the FE. But what it says is that if you know the flow rate of a pump under one condition, you can determine the flow rate of a pump under the next condition depending on if the rotational rate has adjusted, if the diameter has adjusted, and what you'll notice is that it's not always a linear relationship, that some of these terms, for example, are squared, some of these terms are cubed, and so there's a really complicated relationship between if you speed something faster, like for example, if we take up a certain pump and we rotate it 50% faster, that doesn't necessarily mean it's going to add 50% more head, or it doesn't mean that the flow rate's going to increase by 50%. It's a nonlinear relationship. So these formulas allow us to understand how the new pump is going to behave compared to how the old pump was behaving. So the best way, I think, to understand the application of these scaling laws is to apply them in a couple of examples. So I'll handle this first one, part A, to show you this approach, and then the second part of the example I'll turn over to you to try, applying kind of the same technique. But let's say that we have a pump which normally is paired with a 1200 RPM motor, and then the impeller, which is inside the housing, has a diameter of 8 inches. And under those conditions, we know that the pump is going to behave like this. So it has a cutoff head of 12 meters, and then for each unit of flow rate, you can see that there is some reduction of the pump head that's being added on account of the flow rate. So typical performance of a pump. But what we want to know is, what if we change the rotational rate of this system by using a variable frequency drive? Has anybody heard of a variable frequency drive before? We kind of take it for granted that electric motors can be turned up and turned down really easily, but it turns out that that's not the case, that a lot of motors are only intended to operate at a certain fixed rotational rate. And so some pumps, you have to get a really expensive, complicated piece of equipment to change the speed that the motor is rotating at. You have to actually change the alternating frequency of electricity. Like this plug that's on the wall right here, what's the frequency that it alternates back? Alternating current, AC, means it's changing from positive to negative to positive. And do you know what the frequency is of that? How many hertz? Electricity in the United States is 120 volts and how many hertz? Well, somebody's got to know this. Guess. 60 hertz. You didn't know that? That it's alternating 60 times every second. So if, in a 110 volt plug like this, 120, 110 volt plug, one of the lines is neutral, one of them is a ground, and one is the hot plug that's alternating between positive and negative. And it does that 60 times every second. So if you have a motor that is supposed to be rotating at 1200 RPM, the way that we can increase or decrease that motor is by changing the frequency that electricity is alternating. So there's this piece of electronic equipment that can change the power from either, let's say, 60 hertz down to 30 hertz, or I suppose they can also increase the frequency. But let's just say that what we want to do is we want to increase the rotational rate. So we're going to use these affinity laws to show us how does the performance curve change. So what is the new performance curve if we change the rotational rate? So originally, let me, I'll just start by writing on the board and then I'll switch over to the screen later. Okay, so our original rotational rate, so capital N sub 1, is 1200 RPM. And our original diameter, D1, is 8 inches. And the original pump head, H1, is 12 minus 0.1 Q1 squared. Now, this formula didn't say anything about Q1, but what it means is the amount of pump head under condition 1, which is 1200 RPM, and this 8-inch diameter. So the pump head under condition 1 is dependent on the flow rate at condition 1. That's why I've added that little subscript there. Okay? So in part A, what we're saying is we want, under the second condition, the rotational rate N2 to be 2400 RPM, the diameter at 2 to be 8 inches, and then we want to find out what is H2. So we're not changing the diameter, we're just changing the rotational rate. So we're going to find H2. So this top relationship here tells us how the flow rates change when either the diameter and or the rotational rate changes. So the first law is that Q2 divided by N2 times D2 cubed is equal to Q1 divided by N1 times D1 cubed. Okay, so that is a relationship that we've got. Now, since the diameters are the same, we can neglect that out of our relationship because D1 and D2 are the same. So that just leaves us with Q2 divided by N2 is equal to Q1 divided by N1. So in other words, that's saying that Q1 is N1 times Q2 divided by N2. That's Q1. All right. Now, we can put in some numbers at this point. Let me bring up this solution because I think there are a couple of people who couldn't make it today that will probably be looking at this video from home. So we are at close to here. If we put in the numbers, so N1 is 1200, N2 is 2400, then that just says Q1 is 0.5 Q2. So this is one of our relationships that we're going to substitute into the other. So we're going to take this relationship between the flow rate at condition 1 and the flow rate at condition 2. It's going to be substituted into here. Okay? Now we also want to know how not just the flow rate changed, but what's the relationship between the pump heads under this new condition. Okay, so the next part, if we're looking at the next part, it is, we know h2 divided by n2 squared times d2 squared is equal to h1 divided by n1 squared times d1 squared. So where's that from? Let's go back over to here. So this middle set of relationships relates the head on one condition to the head at the other as a function of changing rotational rate and diameter. Okay. So we're not changing the diameter as before. D cancels out. But what we're left with is h2 divided by n2 squared is equal to h1 divided by n1 squared. So in other words, h1 is n1 squared times h2 divided by n2 squared. And if we actually put in the numbers for that, it's 1200, which is our original rotational rate, squared times h2 divided by the new rotational rate of 2400, and square that. So h1 is 0.25 h2. So all of that is equal to 0.25 h2. So h1 is 0.25 h2. Okay, so we've got this. This relates how the flow rates are different when we change the rotational rate. This tells us how the heads are different, and we substitute both into our original formula that relates head and flow rate. Okay, so I'll give you a moment to copy this down. I guess I could erase it off the whiteboard because you've got it on the screen as well. So let me just get a little more room here for our final substitution. Okay, so there is the Q relationship, there's the H relationship, which is H1 is 0.25 H2. And then this is relating Q and H1. So the last substitution is 0.25 H2. So I put that instead of H1 on the left-hand side of the equation. On the right-hand side of the equation is 12 minus 0.1 times Q1, I should say 0.5 Q2, 0.5 Q2, and square that. That's closing. 12. Okay. So we do that substitution. And the new performance curve, as you can see up on the screen, it takes the cutoff head from 12 to 48. So we're getting 4 times as much cutoff head by spinning that impeller twice as fast. And then, ironically, the coefficient in front of the Q remains the same at 0.1. It's not always the case that that would be true. Like if we had also changed the diameters, it wouldn't be. But here, it cancels out. All right, so this is the new performance curve. So those are the scaling laws. Now, how about you try this next one? So this next one, what if the original motor is used? So let's say that N1 and N2 are the same at 1200 RPM. But now D1, the diameter under the original case, which was 8 inches, is replaced with a related pump which has an impeller of 10 inches. So how is that going to adjust the performance curve? You know, are we going to get a nice return on that investment? Like pairing it with a new motor gave us a huge increase in the cutoff head. So how would things change if we just got a slightly larger impeller? So follow the same process where you're going to do the same kind of substitutions as before. You're going to be using this top relationship and the middle relationship because we want to know what is the new relationship between Q1 and Q2. What is the new relationship between H1 and H2? But this time the D isn't going to cancel out, but the N will. Okay, so similar ideas before. Let me pause for a moment, give you some time to make these substitutions and calculations. So this bigger pump's going to cost more money. So what do we get for that extra money? You know, think about how is the performance curve different than the original performance curve, and what does that mean? The original performance curve was a cutoff head of 12, and then the pump head is being reduced at a rate of 0.1 units of head, which would be, 0.1 meters is the coefficient. So look, when we're keeping the same rotational rate, but increasing the diameter, you've got a little bit higher cutoff head, went from 12 to 18, but the real difference is the reduction in that coefficient. So the drop-off of head with increasing flow rate is less severe than it was in the original case. So the curve is going to be flatter. You can get a much higher flow rate without having the pump head drop off quite as much. So the last part of the example asks the question, if you need to pump water 30 feet above the source, I guess we'll assume that this is units of feet for length. If you need to pump water 30 feet above the source, which option is best? The original pump curve, operating at 2400 RPM, or the 10-inch impeller? Well, the original pump curve couldn't achieve a lift of 30 feet because the cutoff is 12. So the original pump couldn't lift water that high, and in fact neither could the 10-inch impeller diameter change, because that can only lift water 18 feet. But if we operate the pump at double the rotational rate, that takes our cutoff head to 48 feet. So we could lift water that 30-foot requirement with the faster rotational rate. All right. So those are the scaling laws. Any questions about the example before we move on? Okay, let's just do a quick blast from the past. The nodal method. Remember when you've got two different flow routes? If you know the water comes into a network and then can either split between pipe B or pipe C, some of the water will go through B, some of the water will go through C. What is the general principle that we apply for solving this? Like, what's the overall concept? of how much water will go through each pipe? Will the same amount of water go through B and C in this case? Just by looking at the diameters and the lengths, can you tell whether the same flow rate will go through B and C? I see people shaking their head in the negative. Why won't the same amount of water go through pipe B and pipe C? Different diameters, different lengths, because there's a different amount of resistance through those different routes. And so the flow rate is going to be whatever flow rate is required so that you have the same amount of head loss through either route. So between junction X and junction Y, you have to have the same amount of loss, regardless of whether you go through the upper pipe B route or through the lower pipe C route. The head loss through each of those paths is the same. And so what we say is that the H sub F through pipe B is equal to the H sub F through pipe C. And that's how we find the ratio of the velocities or the ratio of the flow rates. So what I'd like you to do is calculate what is the ratio of the velocities, and then you can use that along with the continuity equation. So this is one of our big equations in a nodal method problem, is the relating of the head losses through each route. So I guess in plain language, what we could say is the head loss is the same through either pipe. I don't think I spelled that right. Okay, so that's the interpretation of this one. And then the other one, the continuity relationship, is saying that Q in equals Q out at a junction. So we could say QB through plus QC is 0.15 cubic meters per second. So that is our other relationship. And by the way, what is QB? If we broke it down just one step further, continuity equation says flow rate is what in terms of velocity? Velocity times area. So VB AB plus VC AC is equal to 0.15. Okay, so what you should do is have like FB times LB times, if we did it in terms of flow rate instead of in terms of velocity, we could have it QB squared divided by DB times 2 times G times AB squared. Remember that B squared is the same thing as Q squared divided by A squared. So this is just saying have all of that through pipe B equal to FC times LC times QC squared divided by DC times 2 times G times AC squared. So consolidate these so that you've got the B and the C flow rates related to each other, and then with that you wouldn't even have to use this bottom one. You could just substitute it directly into continuity. Okay, find the flow rates and then the pressure at a downstream node. Okay, so here you can see the steps of substituting into the Darcy-Weisbach friction formula all the parameters like the F value, the length of the pipe, the diameter, 2G, the area, and so on. So we get the relationship of B and flow rate in B in terms of the flow rate at C. So which pipe's going to have more flow, pipe B or pipe C? B has more flow. It's a larger diameter, which more than makes up for the fact that it has a longer length. You know, its longer length is going to, in some ways, nudge the flow away from it. But the fact that it has the larger diameter is really significant. So B is 2.67 times the flow rate of Q through C. And collectively together, if we substitute those two together, it's Q sub B plus 2.67 Q sub C. So the flow rate should be 0.109 through pipe B and 0.041 through pipe C. All right. Now, any questions so far about the process of solving this one? It also asked to find the pressure downstream. You're given the elevation and the pressure at one of the junctions. So the way that you find the pressure downstream is you just find out how much head loss is there. So you can put that flow rate into either one of the pipes and determine what's the magnitude of the head loss. And so the head downstream is the head upstream minus the losses. And we need to know the total head. And so the total head includes the elevation head and the pressure head. And so that if we find the amount of head downstream and subtract out the losses, we can find that it went from 565 kilopascals upstream and calculate the new pressure downstream. So, all right, it's 1:50 Friday afternoon. I think it's time for you to start your weekend. Remember that what we're going to do on Monday is talk about the project. So please bring your laptop with that software installed Monday. And then on Wednesday, we're going to have the exam.